Let us see the glacial deposits. We have seen the geological time scale, and one can locate the pre-quaternary strata, that means rocks which are older than the quaternary in age, and if these rocks are glacial deposits, then it has been seen that they are mostly marine in origin. This is an important point. Pre-quaternary glacial strata are usually marine. And how to distinguish the clay particles produced by glacial process from the clay particles coming from the other processes? How to distinguish the glacial deposit? The fine particles in rock flour, that means rock which has been finely crushed due to glacial movement, they do not flocculate and they remain in suspension for a much longer time than clays produced by other beans. Now, one interesting point is that when we say glacial deposit, there is a good chance that this deposit can be a mixture of glacial material and some non-glacial material. In what way? This is the answer here. Streams formed during warmer period in glacial regions also contribute to the transport of the particles. Therefore, some of the particles can be deposited by streams. So, in a glacial deposit that we are studying, we can find two kinds of deposits, glacial and few are stream derived. During the warmer time of the year, the glacier may melt and streams can develop. These streams also can transport particles and can deposit at places. Let us look at a typical continental glacial deposit. We start from the bottom with the substrate. This is the hard rock over which lies till deposits, and as you see in the diagram, tills are generally of different grain sizes. So, it will not be unimodal distribution of any grain size, and there can be good amount of matrix materials over which lies the outwash braided stream deposits. This braided stream might indicate that the glacial period is going away, the region has heated up and streams have developed. Over which lies the glaciolacustrine deposits with verbs. This term verb I have already explained, and it can develop in a glaciolacustrine, the glacial lake mixed environment, over which can lie the lowest deposit. These are the wind blown sand particles and are not glacial products. So, we started from a glacial environment, the peak was here, and then braided deposits, and then verbs, lake like deposits, and finally non-glacial deposit comes here. Let us understand the different kinds of glacial deposits. Supraglacial debris. This accumulates on the surface of glacier as a result of detritus falling down from the side of a glacial valley. Consider this is a glacial valley through which glacier is flowing. Now, in the process of movement, the rock materials might fall in its path, and these are known as the supraglacial debris. We have another kind of debris that is known as the basal debris. What are they? These are entrained by the process of abrasion and plucking from bedrock by moving ice. Consider on this surface ice is moving, then on this surface itself it can pluck off the rock particles, and these particles are known as the basal debris. They are coming from the basal rock over which the glacier is flowing. Now, there is a way to distinguish the supraglacial deposits from the basal debris. The supraglacial debris are dominantly coarse grained material with low proportion of fine grained sediment. The basal debris has a wide range of grain sizes, then they need not be all the coarse grain, and also they include fine grained rock flour. This rock flour comes from the abrasion process. The general term for all deposits directly coming due to ice flow can be called till if it is unconsolidated, and if it has got hardened, then we call it tillite. In other words, when the till gets lithified, it is called tillite. There are other terms, diamicton and diamictite. They are commonly used to describe unlithified and lithified deposits of poorly sorted material. So, the diamicton are the poorly sorted materials which is unlithified, and if it got lithified, it is called diamictite. The term dropstone can be found when we are studying the glacial deposits, a coastal region, and this is ocean water. Here is the till sheet and over which is the floating ice sheet. There can be icebergs. Now, these icebergs can have big chunks of rocks within it, and in the coastal floor region is the laminated mud. Now, these chunks might fall as the ice melts, and these are known as the drop stones. Let us see the glacial stratigraphy. The quaternary stratigraphy is divided into glacial and interglacial subdivisions. When the glaciation happens, we can call the glacial time, and between two glacial periods is the interglacial period. And the quaternary stratigraphy can be divided into glacial and interglacial divisions. Neither biostratigraphy nor chronostratigraphy can tell directly about the glacial processes. Fossils can be studied, rocks can be analyzed for their chemistry, but a very direct link with biostratigraphy and chemostratigraphy and the glacial process does not exist. A single glacial event related deposit can be called as a formation. That means, a lithostratigraphic term can be used to describe a single glacial event related deposit. Formation, which is a standard lithostratigraphic term. As an example, suppose there is a glacial deposit at the bottom, then I can call it a C formation. Over that lies younger non-glacial deposit, we can call it a B formation, and the youngest is another glacial deposit, so we can call it A formation. What has happened? The glacial deposits were designated as formation, lithostratigraphic fundamental unit, and the non-glacial unit also has been named as a formation. This is the meaning of this sentence. Sometimes tills, the glacial deposits which are usually angular, poorly sorted, but rarely they are well sorted as well, reported from some part of the world, and most of the particles are coming from less than 15 kilometer up ice, but this number varies from place to place. This less than 15 kilometer is for some specific area. So, these tills or diamics or diamictons have been studied, sometimes has been used to define the formation, but is also debated. Till deposits can be bedded, so those tills can be called stratified tills. Overall, glacial stratigraphy is difficult to establish. Post-glacial processes sometimes destroy the glacial evidences. This is one of the reasons, but post-depositional processes destroying the original deposition of the sediments is common, not just in case of glacial, but other environments. So, this can be a common case that the post-depositional processes can destroy the original deposition and can create a trouble for stratigraphy, not just glacial stratigraphy, but also in establishing lithostratigraphy, the biostratigraphy, etc. What are the post-glacial processes? Glaciomarine is one, glaciolacustrine, the words themselves tell. For example, after glacial, a marine environment and a mixed glaciomarine environment, lake environment where earlier there was glaciation, glaciolacustrine environment, shoreline erosion, these are some of the post-glacial processes. As I told in the previous slide, till provenance and the grain size distribution have been studied for few of the glacial deposits, but their use in glacial stratigraphy has been doubted and debated. Sediment reworking and redeposition are the problems in glacial stratigraphy. Sediments get deposited due to one glacier, but then that may get redeposited at some other place, and this is a major problem in the glacial stratigraphic studies. The heterogeneity of the glacial sediment is a problem. If you are looking at glacial deposit horizontally, the variation is too much. Earlier we have said a formation can be defined based on lithological homogeneity or also defined by extreme lithological heterogeneity. In this case, horizontal variability can be too much, and that can create a trouble in defining glacial stratigraphy, and this heterogeneity can come even when the entire package of deposition has happened from the same source glacier. As I told earlier, sometimes lithostratigraphic units have been used to describe glacial stratigraphy. For example, formation can be used, and it was shown here. The glacial units in stratigraphy can be diachronous unit, that means they need not be time parallel, not time parallel, and the lowest unit is known as cline. Several clines can constitute a span. Span is of higher rank than cline. Several spans can define a phase. Phase is a higher rank than span and cline. Several phases can define one episode. Episode is of higher rank than phase, than span, and also than cline. So, this way the arrow shows the lower ranks, and this way if I draw an arrow represents the higher ranks. We are not commenting anything whether span or phase is comparable with formation. Stratotype is required in glacial stratigraphy. A type location along with the other detail should be presented while doing the glacial stratigraphy. Same principle we also do in case of lithostratigraphy and biostratigraphy. Two terms are important. We have to understand stadial and interstadial. Stadial is the period of limited expansion of glaciers. Interstadial is the period between two glacial periods, and they are of lesser duration than the Holocene. The duration of the Holocene is 10,000 years. So, the interstadial is of lesser duration than the 10,000 years. Here is an example of glacial deposit that is structurally deformed, and what can we interpret from here can become a good exercise. I would request the students first to interpret this vertical section, and by pausing the video and then check the interpretation. One can locate a fault, and clearly this unit is faulted. I will put half arrows, and if I draw the half arrows here, this indicates a reverse fault. The reverse faulting also is evident here. It is a low angle reverse fault, and again this slip has been observed. These two reverse faults, the red line and this colored line, are actually merging. So, is it a splay remains a question. Within the glacial deposit are these granulations, the field geologist can tell, but they are not the shear zone features. If they were the ductile shear features, the angle between the S and the C planes we commonly expect to be 45 degrees or less. Here the geometry is steep S like this, so they are not sheared. As we go upward, we are finding the layer is strongly folded with low interlimb angle. We can call it tight fold. Here I am finding a sigmoid geometry. Field geologist can tell whether it indicates any shear. In this portion I am getting lenticular boudins, which indicates a local brittle ductile extension. We do not see these boudins in the bottom package here. We do not see the kinds of reverse fault that was found here. We do not see such large reverse faults in the upper unit here, and in this way one can keep on interpreting. Basically, one has to take care of the stratigraphy and structural information together to reconstruct the history. To understand the volcanic stratigraphy, we need to know the primary igneous structures. By saying primary structures, it is meant that these structures are not produced by tectonic deformation. Consider layered rocks, and if any igneous intrusion happens which cuts across the layer is called the discordant structure, such as the dike. And if there are some intrusions which are parallel to the rock layer, such as these are known as seals, and such layer parallel intrusions are known as the concordant igneous bodies. In place of a single dike, if there are set of dikes with similar attitude, they can be called as the dike swarm. Giving you the definition of dikes, it is a tabular igneous rock that cuts across pre-existing structures or the bedding planes. They can be centimeter to kilometer thick. The thickness of hypabasal dikes, that means dikes which are not formed at great depth, neither at very shallow depth, are of the order of few meter. Here is an example of dike from the Deccan Trap rock, where the rock itself is basalt. Within that, a basalt dike is identified. So, here not necessarily the bedding plane is cut, but of basalt another basalt intrusion has happened. So, it is called as dike. This is the interpreted image where the shear senses have been assigned. The shear planes have been documented, such as the y plane and the p plane, but it is not the subject of our study right now. One can look at the research paper for the detail. As per Tyrrell's book, dikes are igneous intrusions that cut across rock layers or the beddings. Now, two kinds of dikes can be thought about: ring dikes and cone sheets. Consider a magma chamber has come close to the earth's surface. Here is the earth's surface. Now, two sets of dikes can be produced. Here C stands for the cone sheets and R stands for the ring dikes. So, the ring dikes, as per this diagram, are dipping opposite to each other, and they are formed at the hinge portion of this magma body. What about the cone sheets? Cone sheets are assemblages of inclined dike-like masses with arcuate outcrops, and they dip 30 to 40 degree towards the center. If I draw a horizontal line, then this cone sheet here, it makes an angle of 30 to 40 degree. So, also here this angle is 30 to 40 degree. If I draw it in a horizontal line here, here is another sketch of a ring dike. Here is another sketch of cone sheet. This photograph is an example of dikes and seals. First, let us identify the foliation. This is how the foliations can be tracked. So, the igneous intrusion that cuts across the layer, I mean these two are dikes, and there are igneous intrusions that runs almost parallel to the layer. So, this is an example of seal. So, also this one. Here is the definition of seal from Tyrrell's classic book. The seals are relatively thin tabular sheets of magma which have penetrated along approximately horizontal bedding planes. But in broader definition, seals can cut across bedding planes which need not be horizontal. Now, we come to the definition of laccolith. These are injected viscous magma, and since it is viscous, it cannot flow laterally, therefore, it piles up and it gives a bun-shaped mass formed within dome top and flat bases. The sketch will look like this. So, here is the igneous intrusion, and it was of very high viscosity. So, it could not flow laterally much, but it piled up and it produces a bun-shaped mass with a dome top. This is the dome top and a flat base. Here is the flat base. Such igneous structures are known as laccolith. Now, let us come to lopolith. These are massive intrusions of basic rocks, generally concordant, and are centrally sunken like a saucer or basin. Consider over large scale an igneous intrusion which is concordant and of this kind of geometry. So, it looks like a basin or a saucer, and it is concordant intrusion, and this is an example of lopolith. Let us take phacolith. These are doubly convex lens like form of igneous intrusions and found within folded rocks in crests and troughs. This is a sequence of folded rocks. This point in the fold can be called as the crest, and these points can be called as the troughs. Now, possibly one can think that hot molten material came in layers and in concordant situation. Now, apply a compression, a buckle folding. In that case, this layer will be folded into series of antiforms and synforms. The hinge areas are the locations of low strain. So, these are the locations where this melt will preferentially migrate and then will cool down, forming the rock. There are other sets of hinge areas in the trough portion, such as here. So, where the igneous melt can accumulate and then can cool down. These structures are known as the facholiths, where melt accumulates in the crests and troughs of the fold. What is a volcanic neck? When the feeder pipe, the pipe through which the molten material was moving, is exposed, such as this one, it is quite tall. Here is a man for scale. We can define volcanic neck in another way, that is igneous masses that seal up the vents of ancient volcanoes. The vents of ancient volcanoes here can be equated with the feeder pipe. They are usually more resistant to erosion. So, in this case there was rocks in the surrounding long back, but they got eroded, and what is left is only the volcanic neck. Let us look at the definition of spatter cone. This is a spatter cone structure. When a volcanic eruption happens, suppose the liberation of gas is not intense to produce spinders, we can see later what is spinder. Large blobs of magma may be ejected, and then that large blob can land up, forming steep sided geometry or structures. In this way, the spatter cones are produced. What is a cinder cone? It is a type of volcano with steep conical shape formed from loose pyroclastic fragments like the cinders and ash. What is the meaning of the word cinder? Cinder means small piece of burning coal or wood, etc. And here is the photograph for your interpretation. Let us see the definition of stock. Suppose within this magma chamber, the roof rock has collapsed. In that case, a stock is produced. So, this one is covered. Let us look at diatreme. These are the downward tapering carrot shaped body of breccia. Breccia means crushed rock fragments, which can be seen within this place, and it is carrot shaped. It is tapering downwards. Here it tapers downwards. How it can be produced? Suppose there is a dike which is not exposed to the surface, and now due to the applied stress of the dike, its tendency towards moving up, the rocks brecciated in this place. In this way, the diatremes can be produced. A diatreme can indicate a subsurface, subvertical dike. One more precise view of the generation of the diatreme is that when the dike has come close to the earth's surface, such as this, the groundwater nearby converts to steam because of very high temperature of the dike material, which has not yet completely cooled down. It leads to disruption. Here is the figure of stock. Let us look at the different kinds of structures produced due to the lava flow. When the hot molten rock material comes on the earth's surface and starts flowing, it is known as lava. Blocky lava or a lava flow, it is characterized by broken apart surfaces of rocks like the clinker fragments, and it has got a rough surface. Here is actual photograph of a lava, and here is the sketch of the a lava. Next one, ropey or Pahoehoe lava. It has a ropey surface, looks like ropes. It can have smooth glassy surfaces also. Here is the example of the ropey lava, where the rope like appearance can be seen very well. This is a more eye-catching photograph of a ropey lava. By saying rope like appearance, these lines are meant, and note that in this particular case there is the next generation lava flow that has cut across the ropey layer. So, two generations of flow at least can be deciphered. One generation was here, and second, here the other generation of flow has taken place. The ropey flow, these kinds of patterns indicate flow towards the convex direction. So, here this is a flow direction and there it is a flow direction. Here is a sketch of the ropey lava. So, from here it originated and it is moving in this direction. These are the rope like appearance, and from concave towards convex is the direction of the paleo flow of the lava. Let us look at the columnar joints. I am talking about these joints. Let us understand them. The columnar joints look like this, ideally hexagonal in plan and column like geometry in vertical direction. This is the plan view and ideally hexagonal. It can be triangular also, pentagonal, in fact can be called as polygonal. And by saying joint, these are the joint surfaces. They are commonly found in basalt, but also in other rocks, not just the igneous rocks, but even in sedimentary rocks such as in sandstone and limestones. The origin of the columnar basalt is not well understood, but one view is that on a horizontal surface, suppose there are different centers of cooling developed in the lava flow, then if I join these two points of cooling by a line and find out the perpendicular bisector, this becomes a potential joint plane. So, this is the surface appearance and it will continue at a depth producing subvertical joint. Suppose these red dots are the centers of coolings, join them by straight lines and then find out their bisectors, and then the column geometry is produced. It explains the columnar joints hexagonal geometry on horizontal surface, but this theory cannot explain the vertical length or this length of the columns, how they are produced. So, for there the double diffusion theory has been put forward from fluid mechanics. Columnar joints need not be all the vertical planes, they can be curved. There are also columnar joints of this kind of curved geometry. Now, we are going to see the pillows. When the basalt erupts inside water, say sea water, then convex up geometry can be produced. This is a pillow structure and it is convex up. In cross section I can draw in this way, and this convex up direction is the Younging direction. So, if a pillow basalt is found of this geometry, that will mean that in the past this was the Younging direction, this is the old direction. In other words, this line has taken a 90-degree turn, which can be due to regional folding. Suppose this is a pillow basalt, then this is the Younging direction, and this situation indicates 180-degree tilt of rock, which can be produced due to folding. Let us look at the term vesicle. These are the gas bubbles which appears as of vesicular geometry on the igneous rock surface. Suppose these vesicles are filled up by secondary minerals, commonly quartz, feldspar, zeolite, chlorite, then the vesicles are given another name amygdals or amygdules, and if it is a basalt host rock where amygdals have been found, the basalt can be called as amygdalodal basalt. Let us look at the pipe stem vesicles and the pipe stem amygdals. The vesicle can be of a pipe geometry, and if it is filled up by secondary mineral, then it is called a pipe stem amygdal. These are the good examples of the pipe stem amygdals. Suppose I am watching on a vertical surface, the gas escape was happening in this way, and here also a gas escape was happening within the basalt. They might get joined together to give a fold like appearance, but this is a tectonic and this can be found in basalts. Let us look at the lava tubes. The term indicates what it means. It can be, it is a tube through which lava has flown. It can be tens of meters in diameter and several kilometers long. Just to give an idea how big it can be, here is an example of a lava tube, and here this much of the aperture is filled by lava now as a volcanic rock. This is an example that from lava tube actually volcanic eruption is happening, and this figure shows the vast extent of the lava tubes. What is a pressure ridge? If a lava tube is blocked or constricted, then pressure builds up leading to doming, such as this figure. Consider there is a lava tube and then within that lava was flowing in the past. For some reason in this place the lava flow has been blocked. So, more and more flow comes inside and it bends the tube in this way. So, on the surface pressure ridge is produced. Now, this pressure ridge can get broken with time, producing this kind of opening, and that is being shown here, that the pressure ridge has got broken in the hinge area.